Hi and welcome everyone. In what ways can the limit at a point fail to exist? Can we somehow make a distinction between these various cases? Let's start off by quickly reviewing the definition of a limit. We say that the limit of a function f as x approaches a is some value L whenever the function values f of x approach this value L as x gets closer and closer to a. We can also define this when we only consider values of x lower than a, in which case we talk about the left limit, or values of x larger than a, in which case we talk about a right limit. The limit of a function at a point is equal to some value L precisely when the left limit and the right limit both exist and are equal to the same value L. As an example, consider the following function. Let's first take a look at the left limit. In that case, the function is given by x minus 1, which, as x approaches 2, goes to the value 1. From the right, the function is given by 3 minus x, and as x approaches 2, the function value approaches 1. This means that the left limit and the right limit are both equal to 1, which means that the two-sided limit is equal to 1 as well. Note that the actual function value at this point, where we take the limit, is irrelevant. For instance, consider the following example. If we consider the left or the right limit, then we are considering values of x unequal to the special value 2. So for those values of x, the function is given by x plus 3, which approaches the value 5 as x approaches 2. So this means the limit as x approaches 2 of the function f is 5 as well, even though the function value of this function is 7 at point 2. So when can a limit not exist? Well, there are many reasons why a limit might not exist. We will consider a few common occurrences. For instance, in the following example, when x approaches 2 from the left, f of x is given by 3 minus x, and then the function values approach 1. While from the right, the function is given by minus 9 plus 2x, which approaches the value minus 5. So in this case, the left and the right limit both exist, but they are unequal. So that means that the two-sided limit in this point does not exist. For this example, whenever x gets closer to 2, the function starts oscillating heavily between the values minus 1 and 1. This means that as x approaches 2, either from the left or from the right, the function values do not approach a single value as they keep on oscillating. Hence, the limit does not exist. The final example is one of the most commonly occurring ways in which a limit can fail to exist. Indeed, if we approach 2 from the left, we see that as x gets closer to 2, the values of f of x become very large negative, which means that the function values do not approach a single value. And if we approach the point 2 from the right, then the function values become very large positive, which means that the limit also doesn't exist. This example is a very typical case where instead of going to a certain number, the function values approach either plus or minus infinity. So let's adopt some notation to handle this. We write that the limit of a function f as x approaches a is infinity when the function values grow arbitrarily large as x approaches a. Similarly, we write that the limit is minus infinity whenever the function values grow arbitrarily large negative as x approaches a. As a warning, even though we write that the limit of the function equals either plus or minus infinity, the limit still does not exist. It is just a shorthand notation to tell you in what way the limit does not exist. Whenever a one or two-sided limit at the point a is either plus or minus infinity, then we say that f has a vertical asymptote at x equals a. Indeed, in one of the previous examples, the function has a vertical asymptote at x equals 2. Let's conclude by considering the two following examples. We see that this function has three vertical asymptotes at minus 1, 1 and 2. Let's take a look at each of these separately. We see that the function is not defined for values of x less than minus 1 because the logarithm is not defined there. Whenever x approaches minus 1 from the right, we see that, because of the logarithm, the function values approach minus infinity. Now we take a look at the second vertical asymptote at x equals 1. In this case, if we approach 1 from the left, we see that the function values go to minus infinity, while if we approach from the right, the function values approach plus infinity. So we can write down these one-sided limits, but there's no way to write down something for the two-sided limit, since it approaches minus infinity from the left and plus infinity from the right. On the other hand, for x is 2, both from the left and the right, the function values go to infinity. So we can write that the limit of x approaching 2 of f of x is infinity. Remember that in each of these cases, even though we can write that the limit is plus or minus infinity, these limits still do not exist. As our final example, consider the following function. We note that the function is undefined at x is minus 1 and x is 0, since we would need to divide by 0 there. In addition, the function is not defined at x equals 1 due to the logarithm. You might be tempted to think that this function has a vertical asymptote at each of these points. However, as you can see from the graph, the function only has a vertical asymptote at x equals 1, and the limits of the function as x approaches minus 1 or 0 simply exist. In the upcoming lectures, you will learn how you can evaluate these limits. That is all for now. In class, you will learn more about limits and asymptotes. So thank you for your attention and see you there.